Hi class, welcome to another review video. I've prepared a practice test for you. I know when it looks like an exam, you sort of take it more seriously. So here are a bunch of problems. You'll notice that the points will add up to more than 100 because I want to give you more examples to practice on. But this gives you more or less an idea of how I will be marking. All right, let's start with orthogonality. We want to use, so the first question, we're given a matrix A, a vector B. Under A, use Gram-Schmidt to find an orthogonal basis Q1, Q2 for the column space of A. Now here A and B are gonna be a little tricky for us because we're sort of using A and B for to mean multiple things. But as long as you give me the right Q1 and Q2, I don't care if you abuse notation, so don't worry about that too much. All right, part A. So if you recall the algorithm, and you really don't have to memorize it, you just need to be efficient in applying it. On the exam, you can definitely look at the formulas. I'm not doing the same thing, so if I make a mistake, well, you make sure you correct me when you're doing your own work. Okay, so we start with two vectors, A, 1, 2, 2, and B. This is just for the Gram-Schmidt purpose. This is how I introduced it. I know I'm using a B to mean different things. Bear with me. This is not the B that is in the problem. It's just how we had set up the formulas, and I don't want to confuse you. I'm sorry that there's a bit of an abuse of notation here. So the process for Gram-Schmidt says A is the same A. So this is us trying to set up an orthogonal basis. And then the capital vector B needs to be obtained from the vector B by removing its projection onto the vector capital A. So that was minus A transpose B over A transpose A times A. Okay, so we just compute what that is, and this is the new B that we have introduced, not the B141 that is in the problem. This is just to be consistent with how we introduced Gram-Schmidt. Of course, you're more than welcome to use different letters if you like. So this B here is 3, 2, 1 minus, as I said, capital A is lowercase a. It's the same thing, so you could replace lowercase a if you like. So I have the dot product between lowercase a and lowercase b here, essentially, which is 3 plus 4 plus 2. So that sounds like a 9. I hope I'm not making a mistake here. I'll double check. A transpose A would be 1 plus 4 plus 4, which is again a 9. And then the vector A is 1, 2, 2. So 9 over 9 is just a 1. So it seems that capital B is the difference between lowercase b and lowercase a. That gives me 2, 0, negative 1. Now, how can I check that I haven't made any mistakes? Well, obviously, this new vector that I've obtained here is a linear combination of this vector and that vector, which means that if I take this vector and this vector, which are obviously linearly independent, I'm going to be spanning the same space. So all I need to do is check whether this vector and this vector are truly orthogonal. If they are, I have not made mistakes. If they aren't, I need to go back and make sure that I haven't made any computational errors. Well, you have 1 times 2, 2 times negative 1. Indeed, the dot product between lowercase a or capital A and capital B is 0. The two vectors are orthogonal, so we know we're good. Now, to find Q1 and Q2, all I need to do is divide by the lengths. So the algorithm says Q1 equals A over the norm of A. Or 1 over the norm of A times A, doesn't matter. What is the norm of A? Well, we actually kind of even have it here, A transpose A, that's square of the norm. So the square of the norm is 9, which means that the norm is 3. So Q1 is simply a third of A. And you're welcome to leave it like this. You don't have to distribute that 1/3 inside the vector. And then Q2 is B over the norm of B. What is the norm of B? So if you do B transpose B, that is 4 plus 1, which is a 5. The norm is square root of that 5. So you have 1 over root 5 times 2, 0, negative 1. You're welcome to leave it like that. This is a perfectly acceptable solution. Okay, now let's look. So we are done with part A. Let's look at part B. It says find the projection P of the vector B. Now let's forget about this A, forget about this B. They no longer exist. Forget about this capital A, capital B. Going forward, you have a Q1 and you have a Q2, and we're going back to this A and that B. So this was us introducing something because that's how we talked about the Gram-Schmidt algorithm. Of course, you could call this a V, a lower V, this a lower W, capital V, capital W, and then do this whole thing with different letters if that's what you like to do. But if you are going to be abusing notation the way I did, make sure you understand that this A is not the matrix A and this lowercase b is not this vector B, although they both represent vectors. Okay, so find the projection P of the vector B onto the column space of A, and there is a hint here. Could you use the new basis Q1, Q2? Well, what is Q1, Q2? So let's go back to A. It says use Gram-Schmidt to find an orthonormal basis Q1, Q2 for the column space of A. In fact, part A of this problem reminds you that when we apply Gram-Schmidt, all we are doing is we are finding a new basis for the same space. So you see, the column space of A is exactly the span of Q1, Q2. It is also the span of A and B here, of the two columns, right? But it is also the span of these vectors. So I could use either basis for my column space, for the column space of A, and I could use either basis to find the projection matrix. So what was the formula for the projection matrix? This is where you need to have your notes handy, and I hope you have been keeping track of your notes. So what I said was that the column space of the matrix A is indeed span of Q1 and Q2. Okay, so I could be using this new matrix Q, right? So if I were to construct a matrix Q, whose columns are lowercase q1 and lowercase q2, so these vectors, the new vectors, then what I have is that the column space of A is the same as the column space of Q. This is what Gram-Schmidt does. You maintain the column space. If you recall, when we did elimination, we maintained the row space, but when you do orthogonalization of the columns, you maintain the column space, but you have a new basis for it. But what is nice about this Q is that its columns are orthonormal, and so we know that Q transpose Q is just the identity matrix. Now, what was the formula for a projection matrix? Well, in the case of orthogonal well, this is not an orthogonal matrix because it's not a square matrix, but in the case when the columns of a matrix are orthonormal, the projection matrix is simply Q transpose. So from here, I immediately have the projection matrix. I don't have to compute many products. And in fact, this is quite nice. This comes out quite nicely. You see, you have Q with the two columns, Q1, Q2. And then you multiply by Q transpose, which has Q1 and Q2 as its rows, right? That's Q transpose. You can carry out this multiplication of these two matrices as column by row, right? You don't have to do it row by column. You can do it column by row, in which case you get Q1, Q1 transpose plus Q2, Q2 transpose. Remember, these are rank 1 matrices, and you have this because you Q1, Q2, well, first of all, that's just not how column times row works. You have to do the first column by the first row plus the second column times the second row, and that's just what you get. If you only gave me this and you didn't carry out any multiplications, it wouldn't be the end of the world. Although, I mean, I would maybe dock down 2 points. So I would give you 8 for this because this is the theory. This is very important. But it's not difficult to compute Q1 times Q1 transpose and Q2 times Q2 transpose. So, okay, let's continue here. You see both Q1 and Q1 transpose will have that 1/3. You can take 1/3 times 1/3, sort of factoring it out. So ultimately we will have 1/9 times 122 times 122. That's from Q1, Q1 transpose. Then from Q2, Q2 transpose, so here is 1 over root 5 from Q2, and another 1 over root 5 from Q2 transpose. When you multiply those two, you get a fifth. And then you multiply 2, 0, negative 1 times 2, 0, negative 1. Rank 1 matrices are very easy to compute. So we will continue with that 9th. We will get a 3 by 3 matrix. Now, remember, when you multiply a column by a row, these numbers just tell you by how much to multiply the column and then to write it as the respective column. So this 1 says just write this column as the first column. This 2 says write this column 2 times this column as the second column, 2 times this column as the third column, and the same idea will be here. You will have 2 times this column as the first column of the result. Then you have 0 times the column, so you will have a bunch of zeros here, and then you'll have negative 1 of that column as the third column. So you don't want to take too much time for these computations. You want to know that this is 1, 2, 2, 2, 4, 4, 2, 4, 4. You always need to get these rank 1 matrices that are of the form Q1, Q1 transpose, or UU transpose, so the same vector being involved, will always be symmetric because that's a symmetric. So this is a symmetric matrix, and this is a symmetric matrix. Then we have plus 1/5 times 4, 0, negative 2, 0, 0, 0, negative 2, 0, 1. You see that's again symmetric. Now, you know what? It's perfectly fine to leave it just here. It's okay. You don't have to go with all those fractions inside. I'm already seeing that projection matrix. Where, by the way, this is the projection matrix onto the line passing through Q1. And this is the projection matrix onto the line passing through Q2, if that is what we want to do. And I overdid it. I didn't really have to find the matrix P. Okay, my bad. I needed to find the projection of the vector B onto the column space of A. Well, good reminder for all of you. So, you know what? I'm going to retract. So I will remove all of this because I don't really need it. I have found my projection matrix. That's fine. So I know that the projection of the vector B is P times B. So that is Q1, Q1 transpose B plus Q2, Q2 transpose B. I can calculate these separate projections one by one. I will not, so it doesn't make sense for me to first compute a matrix when I know that this gives me just a number. So I will compute this number and then I'll multiply Q1 by that number. I will compute this number and multiply that number by q2. I'll add those two vectors and I will have my answer. So I will want to compute like this. Of course, you could first compute the matrices, but that would be a waste of computational time. All right, so because you see the way this works, so let me write it out. Let me write this whole thing. You see from Q1 and Q1 transpose, I have again those 1/3, which I can factor and have a 9th here. Then I can write 1, 2, 2, then 1, 2, 2, and then the vector B, which has components 1, 4, 1. Then 1 over root 5 from Q2, 1 over root 5 from Q2 transpose, I will have a 5th. Then 2, 0, negative 1, 2, 0, negative 1, and then the vector 1, 4, 1. So you see here, this is just easier to do first, and then I'll be multiplying numbers times vectors, which is easy. So that equals 1/9 of 1, 2, 2 times how much? So we have 1 plus 8, which is a 9, plus 2, which is 11. So maybe it's better to, oops, that's too big. So this expression is 11. Let's look at the other dot product. So we have 2 times 1, which is 2, plus 0, minus 1. So we have 2 minus 1, that's a 1 over here. So we see that the answer here is 11 over 9 times 1, 2, 2, plus a 5th of 2, 0, negative 1. And now here it's not a bad idea to put these things together, but if you don't, it's not the end of the world. So you guys can, torture yourselves a little bit to compute those 3 numbers. Of course, you can also use calculators, so although I do prefer fractions. But anyway, that's the solution. Fairly short, not too many computations if you're smart about them, if you use the theory. If you don't, then you can always go through A transpose A, first find X hat, which is the least square solutions, then multiply A by X hat, so you don't have to find the matrix P. But the point here is to take advantage of the fact that you have computed the Gram-Schmidt, that you have applied the Gram-Schmidt algorithm to find an orthonormal basis for the column space that you're trying to project onto. And we're done with B. Okay, now what about C? How is the best least square solution X hat to AX equals B related to the best least square solution Y hat to QY equals B, where the columns of Q are the orthonormal columns Q1, Q2 found in part A. So that Q mentioned is really this Q that we have here, right? So we want to see how the two solutions relate. Namely, if you find X hat and if you find Y hat, how do you move from one to the other? I think I'm going to need a new page, so I'll add that. And I need a vertical one. Oops. There we go. So this is a theoretical thing. I don't really have to go through the numbers, but the point is that you start with AX equals B. And because the projection of B onto AX is not, onto the column space of A is not simply B, it means that AX equals B does not have a solution. So I'll keep track on the left of of the problem AX equals B, and then on the right I'll have QX equals B. Sorry, QY is how the problem had that set up. Meaning that X in the left-hand side and Y in the right-hand side are not the same vector, but B is the same. And the column space of A and the column space of Q are the same. So the way we approach the least square solution, we go A transpose AX hat equals A transpose B. Since the columns of A are linearly independent, we know that A transpose A is invertible. So from here, we have that X hat equals A transpose A inverse times A transpose B. Now, what do we have on the right-hand side? On the right-hand side, we have Q transpose Q Y hat equals Q transpose B. Now remember, Q transpose Q is just the identity matrix, so we have Y hat equals Q transpose B. Now what is the difference between this Y hat and this X hat? If you recall from the Gram-Schmidt algorithm, what happens, so the question is, how do you go from A to Q or the other way around? If you have one direction, you have the other. Well, we know that the Gram-Schmidt process factors our matrix A into a Q times R. Why is R on the right-hand side of Q? So we passed from A to Q, but R is now on the right-hand side, unlike A equals L times U, where L was that passage matrix from A to U. The reason is that L acted on the rows of U to get us to A, whereas here we want to act on the columns of Q to get to A. So you see the Gram-Schmidt, when applied on the columns of a matrix, acts on the right-hand side. If you were to apply it on the rows of the matrix, then you would have an L times Q. If you wanted to orthogonalize the rows of A, you would have something like A equals L times Q. It wouldn't be an upper triangular matrix. Although not the same L that you would get from the LU decomposition, just a lower triangular matrix. Now the point is that this A is the A we started with, and this Q is the Q we ended with. And then there is an R. R has you can compute R. I guess from here, just because we know what A is, you could say that R is Q transpose A. Why is that the case? Because if you multiply both sides by Q transpose, on the left-hand side, Q transpose Q is just the identity, or Q transpose is the inverse of R. So you could compute R as Q transpose times A. You have Q, you have A. This is an easy computation. Now, to be able to connect X hat to Y hat, we have to move from A to R. So let's see how that goes. So we have X hat equals, instead of A transpose, we have R transpose Q transpose. Then we have A, so that's Q times R. Now this is just the identity matrix that's inverted. So we have R transpose R. And then we have R transpose Q transpose. And then we have B. So let's simplify this a little bit. We have R transpose R inverse, R transpose Q transpose B. Now, I know that R is an invertible matrix. This is an upper triangular matrix, which is invertible. So I can compute that, I can apply that inverse and get R inverse, R transpose inverse, R transpose Q transpose B. Now you see this part is just the identity matrix because I have R transpose inverse and I have R transpose. So what I have is R inverse Q transpose B, but Q transpose B is just Y hat. So this part is simply Y hat. In the end, what I have found is that X hat equals R inverse Y hat, or you could say Rx hat equals y hat. This is the relationship that you have between x hat and y hat. R is something you can definitely find. You could also write, now that you know that R is Q transpose A, you could say Q transpose A x hat equals y hat. And going back completely to A and Q, we have AX hat equals QY hat. This is the best relationship that you can possibly find. So this is the best answer. Why is it the best answer? Because you have A and you have Q. So that's how, and I guess we could have started with this from the very beginning. I made a very lengthy explanation. I think I'm wrong here. This is not the best answer. This is the best answer, which tells us exactly where we are. And now I realize there are much better ways to go about this. So bear with me. Obviously, you're not going to have this exact question on the exam because you could copy from here. But a better way is to start from the fact that in both of these, the right-hand side is B. So you could start with, or even the fact that, yeah, you have, I guess just starting from AX equals B and QY equals B, that's not enough because Q is not invertible and A is not invertible. So having AX equals, you know what? I think we're just fine. You cannot simply conclude if AX equals QX, you cannot equals QY. So here's what I'm trying to say. From here, obviously, AX equals QY. But this does not necessarily imply just by default that AX hat would also equal QY hat. You actually have to show it because X hat and Y hat are not obtained in that simple way. So I think we did it just fine the first time. Okay, so this is a very good answer over here, and so is this. The point is that X hat and Y hat are related through that right upper triangular matrix that multiplies Q on the right to get us back from Q to A. Okay, that's enough for that problem. We solved all of these things. And I will admit, part C of this problem was a bonus question when I gave it last year when we did exams in class, and it was meant to push students a little further. So this is a bit of a more advanced problem, but part A and part B are fairly standard. You could solve part B in not the most efficient way, but that doesn't matter. You would still get your marks. All right. Problem number 2, continuing with least squares. Suppose x hat is the best least square solution to ax equals b, and x hat is the best least square solution. Oops, I think I have a typo here. I should correct that. This should be a y hat. Is the best least square solution to ay equals c. Does this tell you the best least square solution z hat to az equals b plus c? If so, what is the best z hat and why? So it's telling me here, yes, it does, or no, it doesn't, is not enough. That's just, you took a 50-50 chance of getting the right answer. For that, I'm not going to give you any marks. What I need is for you to show me what's going on. So you start with z hat. Okay, so I have AZ equals B plus C. Okay, now how do I go to Z hat? Well, I multiply both sides of this equality by A transpose. So I have A transpose A Z hat equals A transpose B plus C. right? I have to multiply B plus C. That's the right-hand side. But on the right-hand side, I could write A transpose B plus A transpose C, because that is how matrix multiplication works. I do have the distributive law and I can distribute that product. So then the question is, what is A transpose B and what is A transpose C? Well, if AX equals B, I know that A transpose AX hat equals A transpose B. And I know that if AY equals C, then A transpose AY hat equals A transpose C. So I will use A transpose B and A transpose C in here. I can replace A transpose B and A transpose C with the left-hand sides, namely this and this. So here I can write A transpose AX hat plus A transpose A Y hat. Over here, I distributed A transpose over the sum. Here I can factor A transpose A out of the sum. So I get A transpose A times X hat plus Y hat. So what do we have here? We have finally A transpose A Z hat equals A transpose A X hat plus Y hat. Now, does this tell me exactly what Z hat is? The answer is no. You cannot simply conclude that Z hat equals X hat plus Y hat. And the question is, why not? So if you have something like this, I'll just digress for a moment. But imagine you have something like this in calculus, x squared equals x. The most common mistake for students to make is to say, oh, so 1x cancels here and I get x equals 1. That's wrong. Why is that wrong? Because you're missing, if x squared equals x, then x could be 0. 0 equals 0 would satisfy the equality. So the better thing to do is to move this x on the left-hand side, write x squared minus x is 0, then factor, you have x times x minus 1 equals 0. And now you see that there are actually two solutions. One is x is 0, and the other is x is 1. Well, you need to do the same thing with matrices. So here I will move the right-hand side to the left-hand side and factor A transpose A. So what I have is A transpose A times Z hat minus X hat plus Y hat equals 0. Now, what I know is that Z hat minus X hat plus Y hat is in the null space of A transpose A. If the columns of A are linearly independent, then what we know is that the null space of A transpose A is the same as the null space, which is always, in every case, no matter whether the columns of A are linearly independent or not, the null space of A transpose A is always the null space of A. But in the case when the columns of A are linearly independent, we know that these null spaces are both 0. And only in that case, we know that Z hat equals X hat plus Y hat. Otherwise, we cannot find Z hat uniquely. Well, we cannot find Z hat using X hat and Y hat uniquely, right? It is related. We know that the difference between Z hat and X hat plus Y hat is in the null space, but that's about it, okay? So the uniqueness is not enough. I mean, the uniqueness is obtained only if you have linearly independent columns. So the answer is sort of yes and no, right? So you could find a z hat using x hat and y hat if you use, using this will work in all cases. You can always use x hat plus y hat to solve the new system, right? To solve this, even when the columns of A are not linearly independent. But when they're linearly independent, you know that the solution is exactly x hat plus y hat. When the columns of A are not linearly independent, then x hat plus y hat is one solution, but there are infinitely many. There are many more solutions. So yeah, the answer is a bit twofold. In this way, you've answered it absolutely perfectly. If you go off of here and you say z hat equals y hat plus x hat, I'm going to give you 8 marks, but I'm not going to give you 10 because you're missing the point that z hat does not always have to be equal to x hat plus y hat. As long as the difference is in the null space here, and you don't know if whether the null space is 0 or not, then you don't know that you have uniqueness. Even if I were to tell you that the null space of A is 0, or namely that the columns of A are linearly independent, I still want you to say that A transpose A times this vector is 0, which means that this vector is in the null space. And since the columns of A are linearly independent, it means that this is 0, because only the 0 vector is in here, and therefore z hat must be equal to x hat plus y hat. Alrighty, you may need to watch this more than once. Okay, let's look at part B, and I'll try to squeeze it in here, so I'll put that over, oops, it's not what I wanted to do. A nice vertical line here so I don't change pages. Alrighty, so here we're going to solve part B. If Q is an m by n matrix with orthonormal columns, and A equals Q times R, where R is square invertible, show that the best least square solution, Q hat, to AX equals B is given by X hat equals R inverse Q transpose B. Now, nobody says here that R is upper triangular. Okay, it is just a square invertible matrix, but that is not important. What is important is that you indeed have invertibility in R, and this problem over here is the same as this problem over here. So this is the same. You can use the exact same logic that we used in problem 1 part C, where we applied the Gram-Schmidt algorithm, and we knew that A and Q are related through a matrix R, which is upper triangular and invertible. But if you notice from the solution that we have here, so I'm not going to repeat part B. Part B is just exactly what is on this page. The key point here is that the only thing that we used about R is the fact that R is invertible. That's the only thing we used. We knew that R was invertible. We knew that therefore R transpose is also invertible. Nowhere here did we use the fact that R is upper triangular. So exactly these things can be applied right here. Now, what is Q transpose B? Q transpose B is exactly Y hat. I guess I'll repeat the arguments. That's okay, because I think you might actually get confused if you try to figure it out on your own. Okay, so we know that A equals Q times R. R is square invertible, so R is square and invertible. Well, actually, it's enough to say that it's invertible because only square matrices are invertible, so okay, that's enough. Now, we want to express the least square solution. So you see, you have AX equals B. Then A transpose AX hat equals A transpose B, and that's how we get X hat. So now we have an equation that has X hat in it. Here, you can already pass to QR, and you're going to be expressing X hat. So QR here, instead of A, then QR X hat equals QR transpose B. So Q is not invertible. I cannot multiply, Q times R, which is A, is not invertible. Why not? Because Q is an m by n matrix. So I cannot assume that A is an invertible matrix. But I can apply the transposition. So I have R transpose Q transpose times Q times R X hat equals R transpose Q transpose B. Now here, Q transpose Q is the identity matrix because the columns of Q are orthonormal. So this is just the identity. I can simplify and say R transpose R X hat equals R transpose Q transpose B. Now I can multiply both sides by R transpose inverse, because if R is invertible, then so is R transpose. I know that the inverse exists. And so essentially I can eliminate R transpose from both sides of the equation because R is an invertible matrix. So this is where we use R is invertible. And so we have Rx hat equals Q transpose B. Multiplying both sides by R inverse, we get X hat equals R inverse Q transpose B as required. Okay, moving on. Okay, something more interesting, still using projections, but a little bit more advanced, I'd say. You actually had this vector x, you had this setup in the previous test. So we have, we're told that the complete solution to some system AX equals B is this vector x. So this is the general complete solution. And C1 and C2 are all possible scalars. We were asked to find to describe the matrix A, to say what is the rank, what is the size of the, like what is M, what is N. And for those of you who solved this correctly, you knew that just from X, we could conclude that A is, is M by N. Actually, what we know is that we have no idea how many rows M has, but we know that it must have 4 columns. We knew that the rank of A is 2. Why is the rank of A 2? Because it has 4 columns, but these two C's say that the null space is of dimension 2, which means there are 2 free columns. And then 4 minus 2 says, 4 minus this 2 says that the rank must be 2, or there must be 2 pivot columns. If the rank is 2, then we must have at least 2 rows. So M must be at least 2. Right? This is what we had on the exam. Now, these are observations that we're not necessarily going to use, but it's nice to sort of familiarize ourselves with the type of matrix that we're dealing with. So we don't have enough information to figure out M. We cannot really work. Now, what does it mean that we don't know M? Now, remember, A has 4 columns. 1, 2, 3, 4. Does that mean that we know the column space, or does it mean that we actually know more information about the row space? What we don't know is how many points there are in here, right? We don't know how many terms are in each column, which means we don't know anything about the column space. I mean, we do know that if we add the first, if we add the first column, the second column, and then minus the third column, we're going to get 0. We know that if we add the first, third, and fourth column, we're going to get a 0. But we don't know how many components those columns have. What we do know is that each row in A has exactly 4 components. That's what we know. So we can talk about the row space. We also uniquely know the null space of A because we have a basis. These two guys give us a basis for the null space of A, right? Okay, so these are all observations that I can make without even reading the question. Okay, part A. Look carefully at X and write down the matrix P that performs orthogonal projection onto the null space of A. So I just said that these two vectors that multiply C1 and C2 give me a basis for the null space of A. So if I have a basis for the null space of A, then I can talk about a matrix P. Now, just from the way the problem is written, it says look carefully at X and write down the matrix P. So this is interesting. The first thing is that I know is that if I have a matrix that, if whatever matrix, okay, backtracking. This is a basis for the null space of A. Whenever we talked about writing projection matrices, we'd always talked about column space, project onto the column space. Now, the fact that this is called the null space, well, just call it a space. It doesn't really matter much. All that matters is that whatever space you're talking about is spanned by these two vectors. So I could very well write myself a matrix B here. I won't call it A because A means something else, but I can write a matrix B that has these two columns spanning its column space, right? So then what I'm being asked to do in part A is to write down the matrix P that performs orthogonal projection onto the column space of B. Now that I have these two vectors as columns of the same matrix, I'm again going to pay attention to this, look carefully. And I see zeros, 0 times 1, 0 times 1, so these two are not important. And then if you pay attention to these numbers, what you see is that 1 times 1 is 1, but then minus 1, meaning these two columns are actually mutually orthogonal. So the columns of B are orthogonal. Well, now this tells me I could get them to be orthonormal even, right? I can normalize these vectors. Sort of Gram-Schmidt is halfway done. The difficult part of Gram-Schmidt is done. What is the norm of each of the columns? Well, the norm of the first column would be 1 over root 3. What about the norm of the second column? It's also 1 over root 3, right? So if I were to actually write not this matrix, but the matrix that has 1 over root 3 in front of it, then I could say that the columns of B are not only orthogonal, but they're actually orthonormal. By multiplying the columns by some number, I have not changed the space that they span. The space is exactly the same. The column space of B continues to be the same as the null space of A. Just because I multiplied these vectors by a number, it doesn't mean anything. But now what I know is that the matrix B satisfies B transpose B equals the identity. I mean, it's not called a cube, but so what? It still has the properties of a matrix whose columns are orthonormal. After I multiplied by 1 over root 3. Before that, I had not my B transpose B was not the identity. It was actually 3 times the identity. But now I know exactly what P is. P is simply B transpose. I can just write it right away. I don't have to do any projections or anything like that. I don't have to multiply a bunch of matrices. If I worked with B, then I would have to also compute B transpose B, because that would not be the identity. I mean, if I worked with this B rather than this one. So not the end of the world if you didn't normalize the vectors, then you would actually have to compute B transpose B and see that it is 3 times the identity. But by making this simple observation that these vectors are orthogonal to begin with, and they have the same length, then it was very easy to normalize both of them simultaneously. Okay, so P is B times B transpose. Both B and B transpose will have a 1 over root 3 in the front, so I know I have a third, and then I have 1, 1, negative 1, 0, 1, 0, 1, 1 times 1, 1, negative 1, 0, 1, 0, 1, 1. I could stop there. Here I've defined the matrix, but remember I could also compute column times row multiplication, and this would not be difficult. So I'll do first column times first row and second column times second row. Both of them multiplied by a third. So the summation will be simple. There may be a lot of writing, but the computations are easy. So maybe I'll factor out the 1/3 from both and then have this big bracket and a sum of 2 matrices. So I have 1, 1, negative 1, 0, 1, 1, negative 1, 0, negative 1, negative 1, 1, 0, and then zeros. Plus, what comes from the second matrix is 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. They are both symmetric matrices, and so I have a third of. I add things up, so I have a 2 here, a 1 there, a 0, and a 1. Then I have 1, 1, negative 1, 0. Then I have 0, negative 1, 2, 1, and 1, 0, 1, 1. A quick check that what I got in the end is indeed symmetric, because if it isn't, I know I've made a mistake. But this thing is symmetric. Just so it's easier to read, I'll shift it a little bit so that 4 doesn't interfere. And that is part A. We wrote down the matrix B. Of course, if you stopped here, I would give you probably about 8 marks, because I'm not seeing actually the matrix. This is what the matrix is. But the computations, they're only lengthy. They are not difficult. How do I compute this matrix? Remember, these ones just say take this column and write it as the respective column. This negative one says switch the signs. This 0 says multiply by 0. So it's all about writing. It's not about computing really. And the addition here is very, very easy. All right. Find the projection of the vector v onto the row space of A. Now pay attention here. This is not the column space of A. It is the row space of A. The matrix B that we talked about in part A was about the null space of A. Now all of a sudden we have the row space. How do we find the row space when we don't know anything about the rows of A? Well, this is where we want to use the fundamental theorem of linear algebra part 2, namely the fact that the null space of A is the orthogonal complement of the row space of A. So actually, if I have the null space, I do have the row space. I'm going to need another page here. So we remind ourselves of the picture of the row space and the null space. So here's the row space of the matrix. Okay. And orthogonal to it is the null space. We have the null space. We have a basis for the null space. We have a projection matrix onto the null space. And so therefore, we really do have the row space. How do we have the row space? We'll take a vector, which is in, so this would be our n, right? The rows of A have n columns. So this is in our n. And we take some vector, let's say V. We know because these two spaces are orthogonal complements, we know that vector V splits into a part here and a part there. So let me say V row space and V null space. So I know from the fundamental theorem of linear algebra that V is exactly the row space part plus the null space part. What is the null space part? Because I already have the null space. You see, if I have the null space part, then I can say that the row space part is simply V minus the null space part. So if I have one, I have the other. How do I find the null space part? Well, the null space part is simply the projection of V onto the null space of A, which is that matrix P that we found in part A times V. So I just have to carry out that multiplication. Let us write that. Now, do I want to use, I could just use the matrix, because why not? Let's copy that. So let me put that here. What I want to write is V sub n equals this matrix times the vector V, which is 1, 2, 3, 4, if I'm not mistaken. Yes, that's what it is. So I just have to carry out that multiplication. 1/3 times, let's see, what do we have? 2 plus 2 is 4. 4 plus 4 is 8. Then we have 1 plus 2 is 3 minus 3, that's a 0. Then we have 0, negative 2 plus 6 plus 4. So that's 10 minus 2, that's an 8. And then we have 1 plus 3 plus 4, that's again an 8. Oh, that's interesting. I did not plan for that. So really I could just write 8/3 if I want. And then 1, 0, 1, 1. Why do I want? I don't know, just looks nicer. So interesting. It turned out to be a multiple of the last column. Okay, make sure you double check that computation, that I didn't make a mistake anywhere, although I don't think so. Okay, so that is the projection of V onto the null space of A. Then the row space part, the projection onto the row space, is 1, 2, 3, 4 minus 8/3 of 1, 0, 1, 1. And I will let you compute those 4 numbers. Okay, that is part B. So we took care of part A, we took care of part B. What about part C? What is the projection matrix Q onto the row space of A? So let's go back to this picture. Can we use anything, by the way, this was part B, can we use anything that we have computed here to find the projection matrix? So what's the idea with a projection matrix? A projection matrix is a rule that is in general, right? It allows us to come up with a rule for projecting in general, not in some special case, not for a special vector V, for a particular vector, but in general. Well, you see, this picture over here is pretty general. I didn't really tell you what the numbers of V are. This is a general setup. So, in fact, from here, we can express V. And if we actually use P times V instead of Vn in here, then I have an expression that only involves V. So let me repeat some of those arguments. What I know is that VR equals V minus Vn, where Vn is the projection of V onto the null space of A. So that is V minus PV. Now, how do I factor V out? V is common to both. You have V here, you have V there. Well, here V, you can think of, I can factor it from the left, from the right, it doesn't matter because it's only V. But here, V shows up on the right-hand side. So if I factor this V out, what do I have left? What you always have left is the identity matrix. So be careful, you cannot possibly write V here, then a P there and say 1 minus. This would make no sense in matrices because this is a 4x4 matrix, whereas this is just a number. So these two things, this is not possible. But what is possible is to write I minus P times the vector V. Now, I minus P is a matrix. Identity minus the projection matrix P is a matrix. It is a 4x4 matrix. And in fact, we see that we get every projection onto the row space, every VR, using this matrix. So this better be the matrix Q. If it's not, we have problems. I do need more space here, so I am going to resize this to something more appropriate. There we go. And now we can just write what Q is, right? We can just say, I mean, we already did. Q is simply the identity minus the matrix P. I already have the matrix P, so I can already have Q. So you would have 1, 1, 1, 1 minus a third of 2, 1, 0, 1, 1, 1, negative 1, 0, 0, negative 1, 2, 1, 1, 0, 1, 1. Now, I certainly don't want to put that 1/3 inside the matrix. That will be too many thirds to write. What I can do is a little trick. So if 1/3 was common to both matrices, it would be easy. But I can't just write 1/3 in front of the identity because that would be a third of the identity. However, if I am to write a third of 3 times the identity, then it all works out. This is correct. The left-hand side is indeed the identity matrix. So then my answer could be 1/3 of, and then I subtract matrices that don't have fractions. So I have, along the diagonal, I have a 1, a 2, a 1, a 2, and everything else stays, well, changes sign really because I have 0 minus. So I have minus 1, 0, minus 1, minus 1, 1, 0, 0, 1, negative 1, negative 1, 0, negative 1. And that is the projection matrix onto the row space of A. So we have actually quite a bit just from that expression X. We were able to find quite a bit of information for the row space and the null space. We cannot find anything about the column space or the left null space except for their respective, well, we can't even find their sizes. We know that the column space has dimension 2, but since we don't know what M is, we have no idea what the left null space would be. So we cannot define A, but we can define 2 of its spaces. Okay, enough for that problem. Now a little bit about determinants. So first question, Very easy. Compute the determinant of A. Now, I want you to all be very careful not to make mistakes. You can use expansion if you like. I personally would not. Why would I not use expansion? Because it seems really, really easy to just use elimination. So that's what I would do in this problem. So not to write that, for the determinant, I'm just going to use these vertical lines, which also denote the determinant of a matrix, but not the matrix. 0, 3, 3, 3, 0, 0, 4, 4. So I will use elimination. I know that if I apply elimination onto the rows or the columns, what I have is that the determinant will stay unchanged. So the operation here will be R2 minus R1 into R2. And I guess I'll make this a little bigger. What we will get is 1, 2, 0, 0. Then the second row will be 0, 0, 3, 0, 2, 3, 4, 0, 0, 3, 4. Now here you have to actually move that pivot up, right? You have to move it here. You don't need to eliminate with it, but you need to move it. So we actually have to do row 2 and row 3 need to be exchanged. And what happens there is that the determinant changes sign. So I have minus the determinant 1, 2, 0, 0, 0, 2, 3, 4, 0, 0, 3, 0, 0, 0, 3, 4. And now I go to the third pivot. I carry out one more elimination step. I'm not going to copy the matrix one more time. Because I have zeros here and 0 there, I know that this 4 will stay unchanged. So in fact, all that's going to happen is I will eliminate that 3. That will become a 0. Everything else will stay the same. You are more than welcome to do that. The answer is then negative 1 times 2 times 3 times 4, which is 4 factorial. You could also just say negative, 12 times 2 is 24. Another way to have done all of this would be from here, you could pass on to expansion. So you can combine methods. You can expand along the second row because you only have one non-zero term. So in fact, the determinant of the big matrix is the same as the determinant of this smaller matrix, which is already triangular, times you have to adjust for whether or not this is plus or minus, and you multiply by 3. So just, this is correct, but I am going to show that to you as well, because I may ask you at some point to use cofactors. So the determinant 1, 2, 0, 0, this is a small detour. 0, 2, 3, 4, 0, 0, 3, 4. So I want to expand along the second row because I only have one non-zero term. So I will essentially be eliminating this part, but I have to worry about that 3. Does it come with a plus? Does it come with a minus? So I start checking. This is a plus, this is a minus, this is a plus, this is a minus. So the 3 comes with a minus. So I know that I have negative 3 times the determinant of whatever is not crossed out. So I have 1, 2, 0, 0, 2, 4, 0, 0, 4. Beautifully, this is already an upper triangular matrix. I can just write what the determinant is, which is negative 4 factorial, which is negative 24. Another way to have done the same thing in 2 steps would have been to first carry out expansion along the first column. So that says that this big determinant is the same as this small determinant. Then carry expansion along the first column there, which would eliminate this row and this column. multiply by that 2 with a negative sign, then 3 times 4. Many ways to get at the same thing. So I could have, instead of gone here, I could have just gone here and then write the answer. Anyway, both are acceptable. This is just another way to keep in mind. Okay, done with part A. Part B. Using Cramer's rule, find the second component x2 of the vector x that solves the system ax equals b. So you think of x as x1, x2, x3, x4. These are the respective coefficients, namely the vector x has components x1, x2, x3, x4. We are only asked to find the second component, not the whole vector x. So if you understand what Cramer's rule does, then you know how to do this. According to Cramer's rule, and I really need you to do this with Cramer's rule. If you do it with elimination, you will get 0 marks because I'm not asking you to solve ax equals b. I'm asking you to apply Cramer's rule. x2 is solved, well, it's a fraction, right? We have a matrix here, a determinant, and we have in the denominator the determinant of a, which we have already calculated, so I'm not going to write that. In the top, because we're looking for x2, I know that the second column of a should be changed. So I know that the first column is exactly the same. I'm looking at the first matrix right here. That's my a. The third column is the same, 0, 3, 3, 3, and then 0, 0, 4, 4, and b is 3, 0, 0, 0. So that's really nice. Why is that nice? Because I don't really want to carry out elimination on this matrix. That would take too long, right? All I have to do here is expand along the second column. So if I expand along the second column, you see here, expanding along the second column would eliminate the second column and the first row. I only have that 3 to worry about, and I'm left with a smaller matrix, which is almost triangular with one simple elimination. But also there is this other point. So what do we have here? Equals. In the denominator, I have determinant a. The sign of that 3, you start always with a plus, and you go up to the point that you're trying to figure out, up to the position where you want to find the sign. So I see it's a -3 times that smaller minor, which will have 1, 0, 0, 3, 3, 3, 0, 4, 4. What I see in this determinant is that the second and third row are the same. So I know that the determinant is 0. So immediately I get 0. I don't even have to worry about more. So I can just say here, put a little note. Equal rows imply determinant is 0. And I'm done. I found x2. All right. So we found A, we found B. What about C? Using the cofactors of A, find the term in the inverse of the matrix in the second row and the third column. That is the entry, okay, I've written it with words, the entry of A inverse in the second row and the third column. We talked about this yesterday, the cofactor formula. So the cofactor formula says A inverse in position 2, 3 is 1 over the determinant of A times the term of the cofactor matrix in position 3, 2. So what I need to find is the cofactor of 3, 2. So what is the cofactor? Now remember that is -1 to the power of 3 plus 2 times the minor that we get from A by removing the third row and the second column. So I know that this is going to be a 3 by 3 matrix that I obtain from removing the third row and the second column. So this is what I'm left with. 1, 1, 0 in the first column. I'll repeat that. Third row, second column. So I have 0, 3, 3, and then 0, 0, 4. 0, 3, 3, 0, 0, 4. This is a lower triangular matrix, so the determinant is just the product along the diagonal, which is 12. And so the cofactor 3, 2 is negative 12. Now I go back to that inverse term, which is negative 12 over negative 24, which happens to be 1/2. If you know what you're doing, this is a very easy and doable problem within, 5, maybe 10 minutes, but not more than that. If you find the whole A inverse, then you've wasted your time. I didn't ask you to do that much work. I asked you to find just one term. And I think that's our last problem. All right. Part A, compute the determinant of this matrix. All right, seems easy enough. Let's do that. So I want the determinant 0, negative A, negative B, A, 0, negative C, B, C, 0. I could do elimination here, which would require a row exchange, but I don't really want to do elimination on a matrix that has A, B, C in it because I'm going to get fractions and I don't really want to deal with them. So the next best thing is to do expansion. It really doesn't matter which row or column you pick here because they each have 2 non-zero terms and 1 zero term. So I'm just going to stick with the first row. The signs for A and B, so I start with a plus, the next one is minus, the next one is plus. So I know how to expand along those first 3 components. What I get is 0 times something, so I'm not going to worry about it. Then negative A times what you get when you remove the first row and the second column. So we have A, negative B, C, 0. Oh, sorry, negative A, negative B, C, 0. And then plus B times what happens when you remove the first row and third column. That's just negative A, negative B, 0, negative C. And this is now really easy to compute because I guess you could have used the lengthy formula, the big formula, copy the first 2 rows over here. I'd advise against that when you have ABCs. I think this expansion business is just easier. I can make this into an upper triangular matrix by switching the 2 rows, which would change this sign if I want to. But even if you use the formula here, this is very easy. So what do I get from the first? What is this determinant? So that would be negative A times 0, which is 0, minus negative B times C. So minus times minus gives me B times C. And here, this is a lower triangular matrix, so the determinant is just the product along the diagonal, which happens to be A times C. And so what I get in the end is minus ABC plus BAC, and since these are numbers, I have commutativity. This is just 0, right? So that's a nice number. I like zeros. Part B. An anti-symmetric matrix is a matrix that satisfies the condition A transpose equals negative A. The matrix in part A is an example of an anti-symmetric matrix. Okay. Find the determinant of any n by n anti-symmetric matrix when n is an odd number. So our A here is 3 by 3. What this is saying is that if you have a 4 by 4 matrix, the same rule would not apply. So it says part A gives you a hint of what the answer must be. So you should focus on showing why the answer must be true. Okay, so we are guessing, this hint here says we should expect that no matter the size of the matrix, as long as it's odd by odd, you should get a zero determinant, because the example in part A is such an anti-symmetric matrix. In fact, it's any anti-symmetric matrix of size 3 by 3 would have determinant 0, because you see A, B, C were chosen arbitrarily. It does not matter what they are. You will always get the answer to be 0. So how can we use this to say solve for maybe the 5 by 5 determinant or 7 by 7 determinant and so on? So let's give that a try. Is there a better way? AC, BC. I'm thinking here. I can't say that I remember exactly what the proof is, so this is really a simulation of what you would do on a test. So what would I do if I were to go, I think I have it. I think I have it. So, okay, let's look at one bigger matrix. I think that will reveal quite a bit for us. So if we look at the bigger one, by the way, the smaller than this would be just looking at this matrix. So you see the determinant of the 1 by 1 anti-symmetric matrix is 0. The determinant of the 3 by 3 anti-symmetric matrix is 0. The determinant of the 2 by 2 anti-symmetric matrix is not 0. It's actually a squared. So here we would have a squared, right? Now, if I have a bigger matrix, what do I get? Oh, I have a feel this needs to be done differently. What I'm thinking of is maybe subtracting things. If we do this row minus that row, what will we get? We will get A, and then B minus C. And then if we subtract, or maybe add, here we would get A minus B, A minus C, B minus C. I think I'm going to go with the 5 by 5 anyway. Okay, 0, A, B, so I'm going to be using these same letters. 0, C, negative C, 0. And then what do I want? A, B, C, D, E, F, 0. Right, so then here we would have negative D, negative E, negative F. And then we would have A, B, C, D, E, F, G, H, I, K, 0. I'm adding too many, don't I? G, H, I, K. No, this is not the answer. I don't feel this to be the answer. If we carry out expansions along the first row, no. Okay, I'm sorry I've wasted a lot of time. What I'm going to do is I'm going to think about this problem and record another video. This appears to be, I think I'm missing the part here. Okay, actually, I'm not going to record another video. I'm going to forget about this here. I am going to look at this condition. I think I've missed this condition. So I have A transpose equals negative A, right? So, of course, this is it. The determinant of A transpose, so if A transpose equals negative A, then the determinant of A transpose better be the determinant of negative A, okay? Because A transpose is A. We know from determinants that the determinant of A transpose is also the determinant of A. So in fact, what we have is that the determinant of A equals the determinant of negative A. Question is, what is the determinant of negative A? What does negative A do? Well, if you have a general matrix, n by n, right? And you've multiplied it by minus. So if I have minus some matrix with rows A1, A2, all the way to AN, okay? The matrix A has n rows, I've multiplied by minus. So then what I have is that this matrix has minus A1 here, minus A2 here, right? All the way to minus AN there. What does this do, these minuses, what do they do to the determinant? So I have, this one is obviously determinant of A, but here, when I'm computing the determinant, all of these minuses factor out. So the determinant of negative A is minus 1 to, so I've taken out n many minus 1s to the power of n times the determinant of A. Now if n is odd, minus 1 to an odd number is negative 1. So I have minus the determinant of A, right? So what have I proven? I've proven that the determinant of A is minus the determinant of A. If I put these two things on the same side, I get 2 times the determinant of A is 0. That implies that the determinant of A must be 0. So this minus here follows from the fact that n is odd. If n is even, then you have determinant of A equals determinant of A. That doesn't tell you much. But here, when n is odd, it does tell you quite a bit. So I guess you saw that, even if you have a lot of experience with linear algebra, you can still stumble upon a problem. Going back to how the problem is phrased can be very, very helpful. All right, that is all for this review.